Swayam Prabha. Digital India. Educated India.
One table, I will share it to you on the WhatsApp group, but for this we have the data here. So now putting numbers, okay, into our discussion, that's the simple objective. If we are, the first problem is a catalytic converter. You all know where it goes, right? Catalytic converter, where does it go? Vehicle exhaust, yes, very good. So this is the data for the catalytic converter. 1 kg it weighs, and it's made of extruded alumina honeycomb, which weighs about 0.5 kg. The overall body of the catalytic converter. It is coated with 1 gram of platinum catalyst. Okay, so it is a low carbon, main thing is low carbon steel, which is 1 kg, and then extruded alumina is 0.5 kg, and 1 gram of platinum catalyst. So if you look at the materials section of material property section of this book, it has listed a lot of these eco attributes what I showed you in the previous slide. What is the embodied energy of different material? Okay, and if they said it's extrusion, it's extruded alumina, it also gives you what is the embodied energy of the different processes, melting, extrusion, okay, and making this different, if whatever be the steps, they give the embodied energy, right? So for now, we are only going to look at materials. So much of material goes into making this catalytic converter. What is the embodied energy of the just the materials part? We can add more to this as we, if we may not have time now, but there is data available, right? At the material extraction stage, what is the embodied energy of this catalytic converter? You know how to calculate it? Embodied energy per kg is given, and the weights of the 3 different materials which go into manufacturing this is given. What is the total embodied energy? It's a simple calculation, right? 323. And which is the one which is contributing most to this embodied energy, right? Simple. Even though the mass of the platinum required is an order of magnitude or orders of magnitude less compared to the steel and the alumina, it is going to contribute to the maximum embodied energy. Similarly, there are carbon emissions given for these 3 materials in the textbook, right? So then you can calculate what is the total carbon emission at the material production stage. Okay, so that is the production stage. Then comes the, you will be learning it even when you're doing the LCA in depth. Then comes the manufacturing stage, how much it went into the, how much of energy went into extruding these, melting these and making into the, or if there is a mold and if you're going to do it through a mold, or how is the coating being done, if it is electrochemically coated, what is the energy incurred in that electrochemical process. All that data we may have to assemble to find out what is the embodied energy during the manufacturing stage. Okay, and then you know the masses, and then you will be transporting it to a car manufacturing facility. Then comes the, that gives you the transport embodied energy required for transportation, right, from the production site to the car manufacturing site, right? And then use life, that's a 4th life cycle. What will be the energy incurred and emissions? In all these three stages, we can identify, right, how much embodied energy, how much energy for manufacture, how much energy emission is going to come in each stage. Then in the use stage, do you think there will be any embodied energy, any energy use or any emission during the use stage? How? So there is some energy because of the electricity consumption. Okay. Over the life of the period of the catalytic converter, you can multiply and say so much of energy is incurred at the use stage. And then when you go to the disposal, end of life, all the processing units. Okay. Okay. In case it goes for recycling, if not, let us look at both the extremes. At the end of the life, yeah. Yeah, so again, there is transport energy incurred to take it to the landfill and put it there. And then the landfill facility itself, no, there is a lot of energy movement of like earth movers. It has to be dumped. It's part of the other waste if it is going to be dumped, but there is energy involved because there are large earth moving equipments, compacting equipments. They have to put the soil, and there's a lot of operations which are happening in the landfill, right? So there is, if you can divide it for per kg of this material, then there is energy incurred even during landfilling. It's not just recycling. Of course, it is less compared to if the other option is if you're sending it for recycling, and if you're going to extract all that platinum back, separate the alumina back, separate the low carbon steel back, that is incurring a lot of energy, and that is also documented in this book. Okay, so it's a very data intensive book, very practical for this materials and the environment concepts what we are studying. So how much energy it takes to recycle platinum, okay, from the material back, okay, how much energy it takes for different materials, how much energy is incurred for recycling, right? So only if we know that, we will be able to work on other understanding, no, why do we need to do recycling? Told you, right? We have to tell the policy makers in that form, in a quantifiable form, why recycling is important. So I often do this problem of cooking pot, a simple example in class, right? So let us do that cooking pot again. I like that example, which is simple to understand. So cooking pot, like your, let's say your a saucepan at home, right? What are the materials which make the saucepan with a handle? So data, yeah, 43% recycled aluminum. That is one option. If it is replaced completely with cast iron, what is the option? And I'm giving you the embodied energy of aluminum alloy, 210 megajoules per kg. Cast iron is 29, and the phenolic material for the handle, 79. So the weight 0.8 kg, I'll put it here. And the handle is 0.1. If it is cast iron weighs 3 times more. 3 times aluminum alloy. Okay. So this is the embodied energy of virgin. We call it virgin material if it is a first time use, and then recycled. Embodied energy of the recycled material is 25 and 8, same units. And typical recycled content, I think 43% for aluminum and 67%. So you have 4 problems. Okay, let me write it down. Recycle content of cast iron is 8. So it's embodied energy of virgin, recycle percentage, embodied energy of for recycling or recycled material. And then mass. Aluminum, cast iron, phenolic. E is 210. Okay, 0.8, 0.1. 3 times, it's 2.4, 0.1. Okay. So for the original aluminum alloy based cooking pot, embodied energy, 176, okay. If it is a cast iron pot, okay. If it is using recycled alumina, okay, and if it is using recycled cast iron, 55, everybody is getting 55, it's some, yeah, it's close to 44. So you can see the difference when you are using recycled material, right? Make sure that you include the embodied energy when your calculations for the recycled material and the percentage of the recycled material. Okay. How many of you have trouble? So for recycling, there is embodied energy, right? So part of the recycled material will have the difference between the two, right? Virgin material minus the energy required for recycling. Okay. The virgin material will still have the original embodied energy, whereas the recycled material will have the reduced embodied energy. This is you can see that even though recycling is incurring a lot of processes and energy, it is not as much as the embodied energy of the virgin material, right? Even for stuff like metals are the ones which is more energy intensive process, right? May have to melt the product, separate them, again cast them into molds and then send it for recycling. In spite of that, it is 1/10 almost, right, for the aluminum alloy. That is the limit partially because of various reasons, right? You cannot use complete, sometimes the product quality will be compromised. There can be regulations for using. So that is also fixed by several agencies, mostly regulatory agencies, how much of recycled content. Let's say even concrete for that matter, if you're going to use recycled aggregate, Indian building codes are permitting up to 25% of recycled aggregate coming from your C&D waste, construction and demolition waste, into your new buildings, right? So it is regulated, and sometimes it is a functional value. You can't go completely recycled. So for various reasons, the recycle percentage is fixed. Okay, so that much of conservation if you're going to use recycled materials. Similarly, you can, if I give you the data for carbon emissions, right? For virgin material, aluminum alloy, so much of carbon emissions are required. Okay, whereas for for carbon emissions happen. During recycling, what is the carbon emissions happening? Then you can find out what is the overall carbon emission of a product made with complete virgin products versus a product which is made with recycled products, right? So that is the savings we get, and that is what we can project to the regulators and say this much of carbon savings can happen if you are replacing so much material. Okay. Similarly, water usage, everything goes down, right? By like 43 percentage if you're going to replace it with the recycled content. Okay. So this can, if you're going to do it for large products with large number of components, okay, buildings, it will make a maximum impact. I think the next problem is on buildings. So you can do it, you can just look at it. I don't know if you will have time to do it. I'll share the data on your WhatsApp group. Maybe you can do it. But it's basically buildings with a lot of embodied energy. You can actually have huge savings. Okay, if when you are using recycled material within the permissible limits of your building code, right? 86 kg of steel, 625 kg of concrete, and 500 kg of brick. So you can work out what will be I'll give you data for all the building materials, embodied energy and carbon emission. Maybe you can take it as a homework and probably share it tomorrow when you come back. Okay. So now it's a rammed earth. You heard of rammed earth bricks? It's getting very, very popular in the sustainability buildings, right? So instead of bricks have a huge embodied energy because of the kilns, high temperature kilns, they have to be burnt, okay, to attain that strength, okay, and the clay is being used, they need to add iron oxide to get the color, okay, and all that. So cement is also very, very high embodied energy. Those of you who know how cement is manufactured, it's a huge embodied energy, right? I told you about plastics going to replace the coal for running those high temperature incinerators, no, and clinkering has to happen. Lime is required, that is mined. So cement has a much higher embodied energy. Okay, concrete. Steel again has a very high embodied energy. So how much, the more percentage of recycled materials which goes into it. Now you have numbers. You can tell even your if you're a builder, if your client, no, if he wants a green building, right? This is how green you can become. This much of recycled material can go into it within the codal provisions, and you can claim a green certificate, right? Platinum rated buildings, there are different LEED certificates are being given. In India, we have other certification methods. So those are all the incentives for people, industry, okay, to adopt it. And for that, you need these numbers. If you want to go for any certification, carbon credits or green certification, platinum rating, all that, we need these numbers. We can't just be telling that recycling is good, recycled materials are good, okay. So that is how these numbers help us. LCA helps us. These kind of simplified systems also help us. Okay, so a lot of data is there. This is all from the book. And different materials, I wanted to show how much of embodied energy is embedded into materials we use on an everyday basis. Right? So These are all the plastics. These are all the metals and their alloys. This is all the ceramics and what comes from the earth. Silicate, borosilicate glass, or embodied energy per unit mass, CFRP. These are all the natural materials down here. Okay, so this is in terms of volume. And yeah, this is again the second life cycle stage, manufacturing. We need to know what is the energy incurred for different manufacturing methods. This will be very useful probably when you're doing your project, the light bulb and other things, how it is manufactured, what are the processes, and then what is the embodied energy for each of those processes. Okay, so, and emissions. Along with this, there is also data on emissions coming from these processes. No, embodied energy, the material is not extracted. The first use only we account for all the mining and extraction, not for the upstream. That's why drawing the boundaries of your LCA is very important. Okay, and that is already accounted for, and you cannot do double accounting. Okay. Yeah, it is already accounted. So it's very valid question, in fact, when I'm going to talk about it very soon. Where do we account for this extra effort and we are taking for recycling, right? Who takes the credit, right? I'll be talking about it very soon. So that was just an introduction on how quantification is done, right? So you can imagine the huge magnitude. We did only small problems, but if we have like 8 attributes. One is the embodied energy, manufacturing energy, transport. Then we had the carbon footprints at each stage. Then we have water usage. So you have so many eco attributes to quantify in every stage for each material. So if you assemble the whole table, that's a lot of data intensive problem, right? And that's what they do. That's what many softwares are developed to do it. You can't do it manually when the number of materials become huge, right? And there are databases. So LCA also does the same thing. Eco inventory, Eco Invent is a database where you assemble all the data required, okay, for each of the materials. Okay, so a lot of tools are there, a lot of softwares are there to do the LCA, and simplified versions like Eco Audit, which is described in this book, can also be used. I wanted to give you the larger picture. We have been talking about materials which are being manufactured in industries, and then what happens at the end of the life and how it comes back, right? And yeah, this is the one I was talking about. So we have 4 different options for end of life, right? I'm going to go here. Landfilling, simplest, you just go dump it in a landfill. The next one is incineration. Okay, the next best thing you can do if you don't have any other thing is incineration. That's what the different countries we had shown. Then comes re-engineering, repair, refurbishing. Okay, then reuse. Okay, that's the best thing you can get to do. And then recycle, that is energy intensive, process intensive, and all that. So each time you do something at the end of the life, you have to see how much it is giving back to us, the effort we are putting in, okay, compared to just dumping it in a landfill. That's no effort, right? You're just going to just dump it. So if you're sending it to a landfill, collecting the waste, sending it to the landfill, there is only some cost incurred, okay, in the for the disposal practices. There are, like I said, there are earth movers, compaction equipment, okay, in the landfill, and then you divide it with the tons of waste which are being processed on a daily basis, okay, and then you get some energy is incurred in the landfill, very little, okay, and it's a debit. You're only incurring energy, okay. When you're combusting it for heat recovery, waste to energy plant, then it's a different scenario. You're there is the incineration plant, there is recovery of heat, and that depends upon the heat of combustion efficiency of uh, the product itself. Okay, so the efficiency, heat of combustion, everything goes into the picture, and you are able to recover some of the heat, yes, energy, right? So there is a credit at the end of the life. You're recovering something, right? Instead of this one, which is only a debit, you're incurring energy to do it. Okay. When it comes to recycle, like what we just said, there is the initial embodied energy. Okay. And then there is energy which is required for the taking it to the disposal site or the recycling site. So that is there. But you are recycling some percentage. R is the percentage which is recycled. Okay. And so you are getting back some of the embodied energy. So that this R, um, uh, which is the fraction of the material which is coming back, right? 1 minus R. End of the line credit. If you're going to calculate what is a credit you can draw because you're doing it, that is your embodied energy for the virgin material minus what is the embodied energy. That is the material you are getting back. Like say we said 46% recycled, and there is some energy. HRC is the energy required for recycling, and this is the fraction which is recycled. So that is the energy incurred for recycling, like what you did in the problem. So the embodied energy minus the energy required for recycling, you are subtracting, and that is the net virgin material, the energy, embodied energy of the recycled material which is coming back into our cycle. So that is a credit again, right? But when you're going for re-engineering or just refurbishing, like changing the battery, you're not replacing the whole product or recycling the whole product, then only that maybe a small 0.1, 10% of the original embodied energy is used to refurbish by changing the battery. Okay, so the amount of credit we are getting back is 90% of the original embodied energy. There's only a little additional energy we incur, right? When you are doing small refurbishing or small repairs. But then when it comes to reuse, what happens? Entire embodied energy goes into the next cycle. Okay, so if the product goes into, if you're looking at series of lives of the product, you can see how much is getting carried on to the next life of the product and why each of these end of the life options are getting more value added as you go down. And now again you're talking in terms of numbers. You're not just saying reuse is good, recycle is not so good. It's not relative terms, but now you're showing it with numbers, right? You're showing it in terms of embodied energy. You're getting back the carbon emissions you're cutting down, water usage which is getting reduced. Everything is reduced, right? So that is the power of quantifying stuff. So this is your waste to energy scenario where disposal, just even disposal, it is a debit. That's why it is shown above the x-axis, the zero axis. So everywhere, every life cycle stage, there is a debit. Okay, whereas if you're looking at, oh, I wanted to draw these on the graph. So if you're looking at waste to energy scenario, there is again, if you're looking, extending the graph, waste to energy scenario, there is a net credit because you are recovering some heat energy, right? So if you're looking at reuse scenario, you're getting the entire thing back. So if you're going to say the material embodied energy is so much, so you're getting, I'm just doing it relative to that, you're getting so much credit back, right? And refurbished scenario, you're incurring some expense, so there is not as much credit, but and in the recycle you are going to incur, so this is waste to energy, this is reuse, this is refurbish, which is going to incur some energy and some carbon emission. When it comes to recycle, probably it incurs a little more energy for recycling and all that. So if you have the numbers, you can exactly quantify how much of this credit you're going to get in the next life cycle of the product, right? So that's what I wanted to show, and people have done this. There are a lot of examples to quantify. If you have all the numbers from the book, you can actually quantify, use those data, material data from the book, the user input. Bill of materials is what are all the materials which go into making the product. Like for your project, this will be useful. Bill of materials, I identify what is the process of manufacture and how much energy is used, what is the transport, how far it has to be transported, what is the use case, end of life, what is going to happen at the end of life. This also should be discussed as part of your project, not just the manufacturing side, right? So what are you going to do with it, and how much is the energy which you're going to get back, how much is the emission. Okay, so potential EOL credit, if you can quantify, there is in terms of energy, in terms of carbon emission. And yeah, this answers the question about what happens. So there is product 1, which is totally made from virgin materials, right? You're starting off with full virgin material product, and then fraction R, okay, is produced. There is recycling happening at the end of the product 1, and then R is the fraction of recycled material which we are getting, which goes into the manufacturing of a new product. Okay, so this new product uses some percentage of its mass from recycled material. Okay, and the remaining from virgin material. HM is the virgin material embodied energy. Okay, and then at the end of the second life of this recycled, the product which is using recycle, again it is sent for recycling, and our percentage is recycled material which is recovered from the product, which goes into the manufacturing of the third product, third generation product, you can call it. Okay, so it goes on and on like this, but who gets the credit? Does the product 1 get the credit because they have taken the effort to send it for recycling and our percentage of material is recycled? Product 2 is taking recycled material, okay, and it is also sending it for recycling. So the credit for this recycled, this cycle of recycling, the amount you have spent, the energy you have spent, the emissions which have come because of this recycling effort which has been made, who gets the credit for it? Product 1 or product 2? 1, 2. There's a debate, right? So what happens to product 2? It is also getting recycled material. It is made from some recycled material, and it is taking effort to recycle at the end of its life. If it is taking credit for the recycled material and taking credit for this, and let's say product 1 has already taken the credit for sending it for recycling, then it is a double accounting, right? Product 1 is also taking the credit, product 2 is also taking the credit for using recycled material. That is double accounting, right? That the balance will be lost, your mass balance will be lost and all that. Okay, so as a rule, there are 2 ways in which people do it, but then as a rule, it has been accepted that If you are using recycled material, like the problem we solved, the cooking pot problem, then you take credit for the recycled material usage, because that is totally under your control. Recycled content method, they call it. Okay, because you know for sure it is recycled material and you know so much percentage you have used in your product recycled material, right? Whereas you are sending it, just like how we are putting it in a recycle bin, the company just puts it in a, sends it to a recycler. He has no control over what the recycler is doing, right? Is he recycling properly? Where is he sending it to? How much of it is going for recycling, and how efficiently he has done the recycling? What is the energy he has incurred for recycling? So all that is not in our control. So it's better to stick to one end where you know for sure that you have contributed, okay, for the environment by using recycled material. Okay, so usually that is an accepted process. So that double accounting is also not done. Okay, so I think that answers your question. All right, so there's lots of data. If you want, you can say. So this is what I wanted to talk to you, and some things on how difficult it is. It's not so easy to do recycling. I thought I'll share some data on what's happening at the here. All along we have been talking about the industry side, the manufacturing side, right? A product is made and so much is reused and all that. At the industry point of view is one, but then at the municipality's point of view, okay, the government who's handling, at the end of the life, everything becomes the responsibility of the waste management person, right? In India, it is mostly the government. It is the government everywhere. They use contractors, but the responsibility of the government. How do they make decisions? How difficult is it to make these decisions on recycling? It's easier said than done, right? So as you look down, as you go down this chart, these are the number of types of materials which end up in the dump site every day. Plastics, paper, glass, metals, wood, food waste, garden waste, clothing, different types of clothing, and also different lookalikes. I would say like a lot of resembling silk saris, you'll see lot of things which has so many different materials. It has silk cotton, it has jari, which represents the silver jari in your silk sari and all that. But as it gets complicated, as more and more material goes into your fabric or into your new materials are started to develop in this leather, in the footwear industry also, like we discussed, it gets more and more difficult to recycle rather than just a homogeneous material. Like a cotton sari is easy to recycle, right? Shred it and it goes back into the production. The fibers are readily available. Same in case of everything. Plastics, we all know, multi-layered plastics, your Tetra packs, your chips packet, they are more difficult. It cannot be recycled, right? There are two things. There is three things actually: upcycling, downcycling, and recycling, right? So recycling is cradle to cradle, we call it. It goes back as the virgin material. You can extract and put it back into manufacture as the same product, goes into manufacturing the same product. Okay, whereas most of the time we are not able to do that, right? We are only downcycling. You can't make the same product. Even paper for that matter, you cannot get the same quality paper, right? When you are recycled paper is different. It looks different. It feels different. Every time you recycle, the quality changes. The fiber, length of the fiber gets smaller and smaller and smaller when you're doing this repulping, and so it's not doesn't go back to the same quality. And then you have a lot of the ink and other things which has to be removed. So much of complications, and so it's mostly downcycled. Very difficult, except for metals and probably glass. Glass is one thing which can be recycled any number of times. right? You can keep on melting and again you get the same glass. You can go back into the same cradle to cradle. Provided like it is the colored glass makes it difficult. If it is just transparent glass, it's okay. Colored glass has to be classified and then you can use it for the same colored bottles and all that. You have to be lot more complication in segregation, and you should have different operations should be different for different colored bottles and all that. So the more complicated the products are, the more difficult it is for recycling. Right? So upcycling, sometimes upcycling happens. Can you tell how upcycling, you know what is downcycling? I told you, right? The quality of material gets compromised, so the value also gets less, right? When you go for the next cycle. Recycle is, we all looked at the values. Okay, what about the upcycling? Any examples for upcycling? Mm. Making seats from tires. Okay, but is that seat more highly priced compared to the tire? The value of the rubber which goes into making seat, is it higher priced or the product itself is higher priced? Or just being used? Hmm. They paint the tires and yeah, that is one way of reusing it. Yeah, that's one way of reusing it. How did it get more value addition? Biomass to chemicals. Yeah. So when you're yeah, when lignin or even from oil, if you're going to extract now, surfactants are being extracted from plastic, waste plastic. Okay, there is a research going on. Yeah, when the value of the product is more than the value of the waste which you're throwing away, then there is a market demand and then it gets streamlined automatically. Yeah, Bindu just brought this is one thing we give our visiting guests, right? This is an upcycled cloth waste based laptop case, right? So this is cotton cloth. We take these cloth from the tailor shops, small bits you get from the tailor shops after that just goes as a waste. It doesn't have any value, right? But when you buy this, it's like a 200, 300 rupees bag. It has added value add has happened to the same cloth material. Okay, lots and lots of examples are there in India. Lot of people are experimenting, lot of startups are experimenting. Flower waste, which we throw away, can become agarbattis. That's become a very nice startup idea. Many people are exploring. Coconut shells are being made and all those things. So there's a lot of upcycling, but everything is happening again in a not in a large scale to generate income and all that. So think we have to let you go soon, so you come back by 1:30. So yeah, paper I wanted to show you. It's one of the best examples in India for recycling. Right, it's a well-established supply chain process, and the industry is also fine-tuned its process to. That is the whole problem. Industry should be open to take recycled material because they have to make changes in their production process. Virgin material, the process and chemicals will be different, whereas if they want to bring in recycled paper to make the same quality paper, there's only small percentage can be added, and then they have to make changes in their processes. So industry should be willing. Government should again be, again I told you in the first class, lot of people have to come together, partnership. Government should facilitate all this cycle of movement of this, enable it with subsidies or no setting up facilities initially at least. So paper, we are doing a great job. Plastic, not so much, except the PET bottles and the thicker HDPE. Most of it is going into landfill. Glass also, because the collection system is not streamlined, unlike Western countries where You can go and return these cases of your beer bottles or whatever. India, most of it is broken, and it's a practice to break the bottle in after you have a drink. I don't know what they get. They break the bottle. So which is a very bad practice, and it goes out of the system, right? So a lot of it is just going into the dump site, and even if it is collected, it is mostly downcycled, because we want colored, there are different colors getting mixed up, glass bottles, before it comes for the crushing. Okay, so downcycling is, it's used for road construction, it is used for various tiles, making tiles and all that. So the value add, only if there is value add, the waste will get out of the waste stream. It will go into the production stream. And that is where innovations are required. Okay. Metals are also, I think traditionally metals, since of their value, it is going into the recycle line by somehow small scale aggregators and recyclers. Okay, or finally it ends up. Packaging is the biggest challenge we have. And yeah, some more data on how much how much greenhouse gas emissions happen when you are incinerating. This is in terms of large facilities. The government has to make these decisions. How much investment has to be made versus how much greenhouse gas emissions. Now they're thinking in terms of greenhouse gas emissions coming from incinerator, from landfilling. And afternoon you will be doing that exercise. As a software called EQT, and WARM will be introduced to you, where you will be at the position of the government and making decisions. If you're sending it to composting, how much will be the total greenhouse gas emission? If you're sending it for biomethanization, what will be your greenhouse gas emission? Because everybody is under the pressure for this, showing their climate action plan, and no, the 2070 the government has promised, other countries have promised 2050 they will reach the goal of the Paris Agreement, right? So many decisions the government has to make. Reuse and refurbishing, how to enable segregation at source. Should we invest on segregation at source? Should we invest on no this is the one I wanted to show. Yeah, centralized versus decentralized. Government has to invest 300 wards in Chennai. So should we have recovery facilities in each of the 300 wards, or should we have a centralized one? So how much transportation is required to go to a centralized facility and then redistribute it? So all those decisions the government cannot make unless they have this LCAs done and they have some kind of numbers to compare, right? That is a value of quantifying stuff. Okay, cost, greenhouse gases, okay, maybe some dimensions of social impact and all that becomes very crucial for the government to make large the decision at the larger scale, right? So I'll stop here. Afternoon we have a talk exactly on what are the social and economic implications, okay, of projects, sustainability projects. Okay, and then followed by that, you will be having a discussion or a hands-on experience with calculating GHG emissions from solid waste management strategies. Okay, I'll stop here.